Hey, how are you? My name's Christopher Pies, and I fancy myself a experienced C++ developer. And today I'm going to talk about smart pointers and the thought process that I go through in deciding which of the smart pointer types that I'm going to use in which situation, or if I'm going to use a smart pointer at all. So way back when I was in college, or just beginning college, I was learning C++ using Usenet on top of the different books that I was reading that I would go and buy at Barnes and Noble, and there started to be some mutterings about ref counting pointers. At the time, the internet was in its younger days, and we had some websites that were popular, like Dr. Dobbs Journal, and I could swear that's where I first saw it. But this website says that it's in the C++ Users Journal, and then Scott Myers wrote this article on ref counting pointers. I know Scott Myers did some writings on it, and I think he kind of led the parade towards smart pointers, because I had some correspondence with him over email when I was fixing an implementation that someone did incorrectly after reading his book. But anywho, things evolved, and so libraries started making their own ref counting pointers. Microsoft COM came out with the COM pointer, and you'd have maybe a doc pointer in some JSON library, an XML library. And eventually, smart pointers became introduced in the Boost library, and Boost still is very popular framework in C++, where we turned for kind of cutting edge ideas, data structures, algorithms. Back then, we had shared pointer in Boost, and later down the line, we had a unique pointer, and I think auto pointer was in there. About C++ 11, all of those migrated into the standard. So now, at the time of this recording, we're on C++ 20. The current standard smart pointer types are shared pointer, unique pointer, weak pointer, and we only have those three. Hey, I just wanted to throw a little edit in here. If you already know how pointers work and how the smart pointers perform their reference counting and how they work and what they're intended for, what the difference between unique pointer, shared pointer, and weak pointer are, feel free to skip this upcoming chapter to the next chapter where I talk about when to use each type, because that's really the meat and potatoes of why I wanted to make this video, but I ended up giving a bit of explanation on each pointer and how it worked, just so that people that weren't familiar would have a little background. Let's go over each of the pointer types. So I will start with just your raw pointer, the pointer that's been in C++ forever. It's just a form of indirection. When I used to explain it back in the lab in college, I don't know if this is a good analogy, you can tell me in the comments, but picture an old suburban neighborhood. Each house has a mailbox. Let's say those mailboxes are addresses in memory. And then the letter inside of the mailbox is the contents. So you go out to your mailbox, you open it, you find a letter inside, and on that letter, there's another address. So then you go walk down the street to the other address, you open that mailbox, and then you have a letter. Hopefully it's not a bill or someone talking about your extended car warranty. This one you won't see so much in modern C++. You'll mostly see this in C APIs, or when you're dealing with old legacy code that works with C. And this is the double pointer, pointer to a pointer. It should be familiar a little bit, because surely you've written Hello World, and if you've written the full explicit version with the having parameters for main, where you're parsing program arguments, argv is a double pointer. Well, it's really a pointer to an array of pointers, with each one of those pointing to an array of characters. So you could have, any number of token strings on the command line that you're passing in. So this is how they represent that. So when you're not using it for double subscript, you might see it used in a C API like this one for get branch name out of the libget2 library. You notice that there's an out parameter here. Well, C doesn't have references, and it doesn't really have the data structures that C++ have, because you don't have classes and templates and all that jazz. So if you want an out parameter and you wanted to be able to set the value of it inside the function and return different things, you could use a double pointer. And I've seen this in other C APIs. When I was starting off, I was interacting with the Windows API quite a bit, and I was learning DirectX, and I saw double pointers all over the place because Windows API is largely C. You might see it even when you're using modern C++ because you still have to interact with C. Sometimes you might go cross-language and part of your project ends up being simplified down to C, at least at some border, before you go cross-language. And in there, you might see some usage of double pointers, maybe. But you're going to have to call a C API from other languages like Python or Java occasionally. Of course, I don't want to say that with 100% certainty because I'm not a Python expert. I played with it for a year, and I was using the C types here to interact with a C API that connected up to my C++ code. And you had to narrow it down in order to go cross-language like that. And it was the same thing with Java using JNI. Had to simplify it down to a C interface. Now, I'm not saying that the cross-language part is going to use double pointers, but whenever you're in the land of C, you know, somewhere in your project, you might see it. Now let's talk about the smart pointer types. With the raw pointers that we've talked about so far, you might be pointing to something on the stack or the heap, and if you've allocated something on the heap, you're going to be responsible for calling new and delete yourself and making sure that whatever you've allocated is being freed. The smart pointer types, you're going to have the smart pointer manage the object for you. It'll keep an internal reference count, and as that smart pointer is copied or assigned to another, it's going to increment that reference count. And then when the smart pointer is destroyed, it's going to decrement the reference count that all the smart pointers to that object share. And when the reference count hits 0, the object that's being managed will be destroyed. And in this way, you don't have to call delete yourself, and it's a little bit less to worry about. So I whipped up a quick example here using shared pointer that we'll walk through. Here I've got this class I called logged class, and this is the object that we're going to allocate and manage. And you can see in its constructor, I'm just going to push out to console created, and then in the destructor, we're going to write out to the console destroyed. Here I've got some class, and its constructor is going to take a shared pointer of the logged class, the manage object, and then it's going to store it. And then down here in main, entry point to the program, we can see I make a shared pointer to the logged class, so our ref count is 1. Then I create another shared pointer. I'm going to call that another pointer, and then assign it the original. So at this point, our ref count is 2, and we have 2 shared pointers to the same instance of the logged class that we've created in the beginning. If you're not familiar with make shared, this is just going to call the constructor of log class and pass any parameters that you have here onto it. Down here, I've scoped a block, and I'm going to pass our shared pointer into some class, and this class is going to store that and take ownership of it. So up here, we've got that constructor. It takes the shared pointer, and notice I did by value here because I want to denote that I'm going to take ownership. Take data. Down here, this is going to call the copy constructor of the shared pointer and then store it. So we've called that copy constructor, the ref count went up 1, and it's still managing that same instance of logged class. So now the ref count is 3. Once this falls out of scope, this is going to be destroyed, therefore its member, the shared pointer, is going to be destroyed. Our ref count is 2. and we exit the program, as the application exits, everything is going to get destroyed, ref counts down to 0, and the object that we were managing gets destroyed as well. And we could, if we wanted to see this before the program exits, we could just put everything into a scoped block. And then we just simply move this up, and the ref count would be 0 before we exit. And if we run this, we can indeed see, let it compile, find my output window. So I've set a breakpoint here, the ref count is 1, and you can see created was called. So the constructor of our logs class got called one and only one time. Now I'm going to step with the debugger. You see, we got this ref count of 2. We've assigned this to another shared pointer, but the constructor still only got called once. We're still managing that same instance. If I step again, still same instance. Another constructor did not get called again. Now we should see the destructor got called, and indeed we see destroyed got printed out to console. And then I'll let the program exit. It's important to point out in our example here that we've got multiple owners of our instance of logged class that's sitting on the heap. Main is an owner, and then some class is an owner. Unique pointer works largely the same, except that you can only have a ref count of 1 at most. You can't make copies of a unique pointer, and this guarantees that there is one and only one unique pointer that's pointing to that object on the heap at any time. In other words, there can only be one owner, and ownership is important. You can see that IntelliSense is already complaining here that we're trying to call a copy constructor that doesn't exist. It's been deleted for unique pointer. So this example isn't going to work. So if we can't make copies of unique pointer, then how do we pass it around? Well, there's only one instance where you want to pass it around, and that's when you're transferring ownership, because there can be one and only one owner. So if I own it, and I want to give that ownership to you, I have to relinquish ownership in the process. To demonstrate that, I've whipped up a quick example of dependency injection here. I've created a network client that's got this set of functionality. This isn't real world, it's just for example. And then I've made a concrete class, ActiveMQ client, that implements network client. And indeed, we've implemented that interface, although we've just used empty functions here to keep it simple. And then here, I've got an order processor that wants a network client, and it's going to store that network client and take ownership of it. And through the lifetime of the order processor, it's going to make use of that network client. So down here in main, we allocate our ActiveMQ client on the heap. We make a unique pointer out of it. And we're going to transfer that ownership to the order processor. We do that through move semantics. Because this is an L value, it's not going to let us just call this without the move. If it was an R value, then we wouldn't have to move. And by making the constructor of the order processor like this with the double ampersand, we're forcing the caller to acknowledge that they're going to have to move that L value. This double ampersand, when a developer looks at that, they say, oh, you want me to move that unique pointer. So some people might argue that they don't want to make it part of the order processor constructor to take a unique pointer as a parameter. They might want to take a raw pointer. And they might argue, well, I don't know if there's only going to be one instance of the network client and who's going to own it. Maybe it's going to be shared. Maybe multiple components are going to want to make use of that network client later. And we don't want to have to go back and change the code. Well, I'd argue that it's really important to do the design work up front to where you know the relationships of the different objects that you're about to implement. If you haven't worked out your design enough to know who's using this network client and what its lifetime is, I don't think that you're ready to go and implement those classes fully. If you do your design work before you go code and you have an idea what these class relationships are, your life's going to be a lot easier and there's going to be a lot less rewriting code. So finally, we come to weak pointer. Weak pointer only has one scenario where we want to use it, and that's to break up a cyclic reference. I've demonstrated that with some code I have on screen here where we've created a class to represent a person, and we gave each person a name, and we're naively giving it the ability to set a mentor. We're going to track a teacher-student relationship here by calling this method where we set the mentor to a shared pointer of another person. Down here in main, we've got our friends Jack and Jill. They really didn't know what they were doing or how to get water or even put it in a bucket, but to demonstrate what happens without setting the mentor, we'll just run this real quick. And we can see Jack and Jill were both created, and then Jack and Jill were both destroyed. Great. But once we call that set mentor method, which is going to take a shared pointer to the other and retain it here, its member data, neither one is going to be destroyed, and that's because their ref counts can't hit 0. Jack has a reference to Jill here through that shared pointer, and Jill has a reference to Jack through that shared pointer, and the ref count is 1 in both cases. It never hits 0, even though these variables went out of scope. You'd expect them to be destroyed, but they're just going to linger forever. And that's where weak pointer comes in, to break up that cyclic reference. So I've went ahead and fixed the situation by changing that shared pointer to a weak pointer here. The assignment doesn't change. We can still get a shared pointer to another person, and we assign it to the weak pointer, no problem. I also wanted to demonstrate, well, if we want to use the object that's being pointed to, how do we do that? It's going to be different now that it's a weak pointer. If it was a shared pointer, you could just call it directly and call some method on it, and it would be fine because you know that that shared pointer is valid. But with the weak pointer, it's not keeping the object alive for you, not until you lock it. And because we're using weak pointer, we don't know if the object has already been destroyed before the lock, but we do know that it's not going to be destroyed after the lock if it was valid. So what we're getting here is a shared pointer that's got its incremented reference count, and because we have a shared pointer, as long as that shared pointer exists, that object's kept alive. However, if it didn't exist before we did perform the lock, then we can't get a shared pointer to it because it's gone. So I've just put this statement here that says, the mentor's no longer around. If it was valid, we're going to get the name. Now keep in mind, like, this is not how you would design the interface for these objects. This is just for demonstration on how the weak pointer works. Why would you get this sub-object's name from the parent's object? Why not just put a method directly on the sub-object? So just ignore that. I'm just trying to demonstrate how weak pointer works. Let's step through the code with the debugger and verify that things behave as we expect. Now that we've broken up that cyclical reference with the shared pointer by using weak pointer, I'd expect Jack and Jill both to be created. We're able to set the mentor for one to get the other, display both the mentor names, and then when they fall out of scope here, they should be able to be destroyed. Let's see what happens. Okay, we're right before it goes out of scope. Step over, and there we go. They've both been destroyed. And then I also want to demonstrate that block of code where we used the pointed to object. So here, I'm going to reset Jack, and that means when we get Jill's mentor name, Jack has already been destroyed. Let's see how that works. Hit my debugger button, sorry. So Jack is reset. Here we try to get a lock to Jill's mentor. It's empty, so it's going to say Jill's mentor is no longer around because we got rid of Jack. See, Jack has been destroyed. Jill's mentor is no longer around. Step back out, and now Jill should be destroyed as well. So we've got to talk about the get method that belongs to shared pointer and unique pointer. You're often going to be in your code base, maybe you've opted to use a smart pointer type, either shared or unique pointer, and you're going to want to call third-party code or another library in your organization that you don't have control over. And maybe it's asking for a raw pointer to the type that you're dealing with. Well, a lot of programmers, they're just going to see that get method and they're going to call it without any consideration of the effects. And in some cases that works out okay, in other cases not so much. So I've got two examples here. I've got this function called db_insert_person, and we can look at that function, read its documentation in the real world, and we would see, okay, it takes a raw pointer to a person, but it's not taking ownership, and it's not going to try to release that resource. All it's going to do is act on it and then return. So we're just giving db_insert_person a temporary copy of the pointer to a person. It's not storing it. And that's really key. Is there storage? Is there ownership? Is there an act on the lifetime of the thing that we're passing in? Here, I've got another case where we've got a record. And this record, in its constructor, it's taking a raw pointer to a person. In this case, the record is storing that raw pointer. And we don't know what the lifetime of the record is. Well, we do because we have a really super trivial example, but let's pretend we're out in the real world and this is happening in a really large code base. What you're going to have to do in this case, because you got the underlying pointer, and when this shared pointer goes out of scope, it's going to delete that resource. It's still managing it. You've got this copy on the side that you're responsible for. And that's no good when it's stored, because now your responsibility has grown over some length of time. You are going to have to make sure that this record's lifetime is over before the lifetime of this object on the heap that's being managed by the shared pointer. In other words, if Jack goes out of scope right here, let's say we did Jack reset. Oops. Now he's out of scope and it's been deleted. Let me reorganize that. And then we tried to do something with the name. Well, this is not going to work. Jack's gone. We've got this pointer that we obtained using get, but Jack's no longer there, so we've got an invalid pointer. A lot of you might be thinking at this point, oh my goodness, Chris, this is so complicated. There's all these pointer types and all these gotchas we have to remember. Why can't we just make things simple and use a reference? Well, I agree with you, and it ends up so do the people that wrote the C++ FAQ. You should use a reference whenever you can, except when you can't. When can't you? It's whenever there's reseeding. And reseeding means changing the value of it, what it's pointing to. So often you'll have a pointer that's sometimes null and sometimes it points to something. It's being reseeded. You can't do that with references. It's got to refer to the one thing and you can't change it. So this C++ FAQ, this has been around since I started learning C++ on Usenet. It's a great resource. Some of what I would call the greatest C++ minds have contributed to it and rehashed it, and it's evolved over the years. Use this to find the verbiage, examples, the logical reasoning behind a lot of things that you might see on a code review that you know is a code smell. You know this might not be safe, but you're not really sure why. Look it up in the C++ FAQ. It's going to teach you more by working through the logic and the examples, explanations, but it's going to help you to express to your peers your reasoning why you think some portion of the code might need to be done a different way. So a problem you have to watch out for if you're going to use references in any kind of inheritance scenario, you can sometimes, but you have to be careful of object slicing. And so I've whipped up this demonstration to show you the pitfalls of object slicing. I've got a base class, just take some integer, and it's going to spit out, I'm a base class with the value of whatever you gave it. Derived class is going to do the same thing, take some integer, but it's going to set the base class data to 10 always, and then it's got another data member that it's setting to the value that you pass. Similarly, it spits out, I'm a derived class with the value of whatever you gave it. So here, I've got a couple functions. One is going to take a base reference. The other is going to take a base by value. And both are going to speak. And then down here, the third case is where I just declare a base and I try to assign a derived to it. Let's see what the output is and if it matches what you think it'll be. So here in the first case where we had a base reference, we're getting 7, and that's the value we expect. That's what we gave the derived class. The next one, where we call a function that takes a base by value, we're getting 10. The object got sliced. Over here, where we declare a base and we assign it to excuse me, I'm about to cough. We assign it a derived, we also get 10, and this was sliced. So next up, I want to talk about the different considerations that we should think about when we're choosing which smart pointer type we're going to use and where we're going to use it. The first thing that we should think about, and we should think about this on all the C++ objects that we put on the heap, is who owns it? Who owns the object? There should be some concept of an owner. And then we need to think about, well, what is the lifetime of that object that we created? Is it we create it, we use it, and it's gone? Is it going to live as long as some other object lives? Is that other object the owner? Does it need to live as long as another object lives because that other object is dependent on it? Who's going to destroy it? At what point is the destruction of that object going to be triggered, and what is the condition? And then lastly, we can think about the different places in our program where we could use the smart pointer to express our intent. And here's a real good example of that is in this fictitious example that I made up of a little piece of a system. We've got the application starts up, it reads a configuration file, and it decides what is the network connection that we're going to use. We're going to create this to support multiple customers, and each one of those might have a different kind of endpoint. So we put it in a configuration file that, hey, customer X has network connection type Y, and this factory would read that configuration or part of that configuration and create the concrete type of network connection. So this factory, when it allocates the concrete connection on the heap and it's going to give it back to you, that's a real good example of expressing the intent. The factory method should return the smart pointer type, and then the developer knows when they look at that method and they can see, oh, I called create and it returns a unique pointer. It allocated something, and now I'm going to take ownership of that if we decide to use unique pointer. And here in the same example, we ask, well, who's the owner? Going back to those questions we ask, who owns the network connection after we make it? We could have this wrapped QT socket, or we could have this active MQ adapter, and we're going to make one of those from the factory, and then we're going to give it to this data collector. So in this example, all we can see is that this data collector is the only owner. And we could ask ourselves, or whoever's designing the software, is there just going to be one instance of the data collector? Is that all that we're going to have, or is there multiple instances of the data collector? And if so, are they going to share the network client that we made, the network communications? I would say no, because we have this concept of connecting and disconnecting, and we'd probably want to be able to connect to one customer at a time. We wouldn't just connect to 1,000 at a time. So the data collector is indeed the only owner of the network comms class that we're going to give it. What is the lifetime of this network comms class? Well, the lifetime is tied to the data collector that's using it. And looking at this diagram, without anyone to ask questions, I drew it, so I know what the intent was, is that we're going to make a data collector when the program starts up. It's going to read a config file. The factory will make one. We give it to the data collector via dependency injection, and that data collector lives for the lifetime of the application. When the data collector dies at the shutdown, then the network communications is going to go away too, the underlying network comms class. So the lifetime is the lifetime of the data collector. The owner is the data collector. So this is a really kind of simple example here. The data collector is the maintainer as well. The data collector will be responsible for making sure that this network connection is destroyed. And that's really simple here, because when this goes out of scope, this is going to go out of scope too. We might need to make sure of some things though, because this is a network connection that we disconnect gracefully. We don't want to just destroy this object and then have the network communications destroyed and have the person on the other end think that we had a shutdown that wasn't graceful. So we still need to probably have some kind of destructor and make some calls and make sure that things shut down gracefully. So this data collector is the maintainer. And then we've answered all our questions. We know what kind of smart pointer we want to use. Well, there's only one owner, and they're maintaining it, and the lifetime is tied to that owner. So we can use a unique pointer, and it would be fine. I've made another fictitious design diagram that's super simplified, and we just want to talk about smart pointers really, so I don't want to go into the details of what it would take to make a whole ordering system. But here we have the simplified example where a user is going to make an order, interact with the front end. In our process, we've created some kind of HTTP service that's going to have a publish subscribe piece to it. And whenever the customer makes an order, this publish subscribe mechanism is going to notify components that are interested and want to be notified when an order has been created. So I've got this inheritance diagram here where we've made an order subscriber. Here's what that interface is going to look like. We're going to say on order received, you get a shared pointer to an order event. And you can see that I've got a MySQL communications piece that goes and talks to the database, and we'll assume that that's going to make a record of the customer's order whenever an order event occurs. And then we've got a logistics controller piece here that goes and does the physical things in the warehouse to go and fetch that order and make it ready. If you're not familiar with the publish subscribe, it's a design pattern that's used very widely, and it's basically event-based, that you'll have a number of components that are interested in some event that happens, so they subscribe to that event, and then the pub sub mechanism notifies them via a callback whenever that event occurs. So in this case, we're interested in knowing when orders are created, and the pub sub mechanism will call this method from these subscribers whenever an order takes place. Whoops, I noticed I was covering the front end there with my noggin. Let me move that out of the way. So let's ask ourselves the same questions that we asked before. When we create an order from this pub sub mechanism, who is the owner? Well, we probably can't tell from this diagram, and we'd have to rely on some design discussions that we're hopefully having before we go and implement this. And I'd ask the designer, hey, is this logistics controller, is this going to store the order in any way when this callback occurs? And the answer is no. We just want to extract the details out of that order that we're interested in. We don't necessarily need to know the customer, their address, their history, all of that. We just want to know the order items that are in the order so that the physical things that need to happen in the warehouse can happen. So when this callback occurs, it's going to process that order and then it's going to be done with it. We'd ask the same question on this database piece. Hey, is the MySQL comms, is it going to store that order at any time when this callback occurs? And again, the answer is no. We just want to extract the details that we're interested in that need to go into the database to signify that the customer made an order. So we're going to get the order items and we're going to get the customer ID, and that's about it. Stick it in the database, and then we're done. So who is the owner? There is no owner in this case, and this is a really good scenario to rely on the smart pointer cleaning itself up because there's no one there to own it or maintain it. Now let me go off on a tangent a little bit. If this pub sub was not an asynchronous mechanism and was instead synchronous, where pub sub would call logistics controller with the order event, wait for logistics controller to finish its processing, and then in turn call MySQL comms, wait till MySQL comms has done its processing, and then destroy the order that it created, pub sub would be the owner. But we don't want pub sub to sit and wait for the processing of the order. It's just going to call this notify and return immediately, and then these guys are going to do their processing while the published subscriber continues on about its business doing other things. There could be other events that it needs to publish besides the one order. Or perhaps orders are just coming in at a really rapid rate and it needs to keep on dispatching them, in which case these guys are going to process them and try to keep up. Something will have to be in place. Anyway, going down that tangent, I just wanted to point out that pub sub could be the owner if it was synchronous, but it's asynchronous, so no one's going to own that shared pointer. And the same question, who's going to maintain it? Well, nobody's going to maintain it. These guys are just acting on it, and then they're done. Is there any clarity in the code that can be gained by using the shared pointer? I think yes. When these callbacks occur, we know if it's a shared pointer that something has been allocated on the heap. Even though these guys aren't responsible for cleaning up, they know that, hey, this object has a lifetime and I need to finish doing my processing before that lifetime is over. So in my opinion, it helps to note that a little bit, whereas if it was just a pointer, maybe someone here would assume it's going to be alive forever. Maybe they would send it off to other people. I think with the shared pointer, it's more clear that this has a limited lifetime, and at least I, in my opinion, would be prompted then to go and ask questions about how long is that lifetime. So this would be a good case for shared pointer. I don't see using unique pointer here because we want to dispatch it to multiple people. I don't see using a raw pointer here because we want to make note that this has a lifetime and that it is going to go away. There could be a case for that. You could, if this was synchronous, you could get rid of putting it on the heap altogether and put it on the stack and just call these one at a time. But again, that wouldn't be the most efficient system. In this example, I want to talk about just a simple function call. Let's assume we have some system, maybe it's got a UI and some form that the user filled out, and we put together a C++ class out of the data. And in this case, it's a person. And this is a super simple person. All it has is a name. Alternatively, maybe we have a person object floating around the system, came from somewhere, and we're about to send it over the wire, and we want to validate it. So our task is to write this validation function. And here I've got a isValid. It's just going to check the size of the name and return true or false. So the question is, if the person is already a shared pointer elsewhere in the system. We know that it's floating around as a shared pointer. In this case, it's just in main, but picture a large system with many components. Maybe it came from somewhere else, came from your UI, and it's already a shared pointer. Do we have to make it a shared pointer in our validation function? And I would say, no, we don't have to. We could make it a shared pointer right here, but it's not necessary. And if we ever go and change everything up above, then we don't have to change this if we make it a raw pointer. Is it dangerous to use a raw pointer here? No, as long as we still think about all those questions that we've been asking. Who is the owner? Well, in this case, main's the owner. Is the object going to be alive for the duration of this function call? Well, yeah. You wouldn't be able to call this function in a synchronous manner with a valid person object without it staying alive until it returns. The question would make more sense if we were taking that and we were storing it, or if we were handing it to somebody else. Then we don't really know. We have to analyze further what is the lifetime of the person. But in this case, it's very simple. It's, we're going to have a valid person at the beginning, assuming the caller calls us with a valid person. And notice we do have a check here, just in case. And if it's valid at the beginning, it's going to be valid at the end, because this is going to run synchronously and someone's waiting for us to return. So I just wanted to demonstrate you can use a raw pointer. Just because the shared pointer exists elsewhere, it doesn't lock you in. And a lot of people have that thinking, especially junior programs, when they learn something new, they tend to use it everywhere and adapt this rule that, well, the new thing is better, therefore I must use the new thing everywhere. Don't fall into that trap. You don't have to use a smart pointer everywhere. It's perfectly okay to use a raw pointer. When I went to college, we had a class on linked list, and one of the students in the class, every assignment from that point forward, every data structure had a linked list in it. And it just blew me away. Like, okay, we learned linked list. We don't make everything a linked list. We learned if else. We don't put everything in if else statements and keep on nesting them on and on. So don't fall into that trap. You can still use a raw pointer. It's still perfectly valid. Just think about those questions that we've been asking. For the last example, I wanted to bring up the case where you want direct control over when to delete the object. While we could go through this example and think about all those other questions, this one is a little bit different, because we want to implement ourselves the very thing that the smart pointer is offering us, which is the automatic deletion of the object when we're done with it. So in this scenario, let's say we're on an interview, and the interviewer, like so many before them, asks us to implement a linked list. They might give you some boilerplate code that looks something like this, and they want you to implement this insert method and this erase method based on an index. So if you remember the last time that you implemented a linked list, or maybe you just studied it out of a book, or you have to think all the way back to your college days, you might recall implementing some structure that represents a node, and in that structure you probably have a previous or a next pointer. And then you have the data item. Well, you might have this urge to show your interviewer, hey, I know smart pointers, and you want to show off a little bit. So instead of making this a raw pointer, you might reach for shared pointer or unique pointer. But keep in mind, when you do this erase, you're going to be deleting that node. So as the developer, you're doing the very thing that the smart pointer is offering you. And I would if I was interviewing you, I would actually subtract points for you trying to use a smart pointer here, because it shows that you didn't really fully analyze what's going on when you're developing this data structure. Someone might also think, well, using the smart pointer is safer. Well, is it? If you implemented this data structure correctly, then you've correctly deleted the object when you're done with it. So there shouldn't be the scenario where the object goes undeleted and the smart pointer has to clean up for you. And on a side note, if an interviewer asks you to implement a linked list, don't come back with something like, well, why do I have to implement it? I'll just use the linked list out of the STL. Or I've never seen a linked list used. Nobody uses a linked list. Because you're just going to, at least if I was interviewing you, open yourself up to a barrage of questions about, what is contiguous memory? What's a CPU cache? How does that work? What scenarios would you want to use a data structure that doesn't use contiguous memory? What are some scenarios that you can think of that a linked list would be appropriate? And all that's time that you could spend writing code and writing good code. Usually in an interview, you're very pressed for time. Even if they have you implement something super simple, you could always write more test cases. You could put comments. You could pretty things up, make sure it's consistent, make sure your formatting's good, all those things. And I don't know about you, but in an interview, I am always racing to show the interviewer that I know the things that I know. I want to put good test cases on the end. I want to impress them. So use that time to impress your interviewer rather than making snarky comments. Anywho, I think I'll go ahead and wrap things up there. I hope you found some of this information useful. This video went a little bit longer than I intended. I might have got sidetracked once or twice. But yeah, thanks for hanging out, and we'll see you on the next one.